Hi, today I'm going to talk about some applications of X-ray absorption spectroscopy. I'm going to share with you 3 examples, and all of them are my PhD works, and they're about in situ self-studies of nanoparticles under synthesis conditions. First, some background. I joined the PhD program in 2007, and back then, making nanoparticles was very popular but challenging. Here are some challenges listed in the DOE report. As you can see here, first, it was hard to precisely control the size and composition of nanoparticles. Second, it was difficult to manipulate their positions. Third, it was hard to scale up their synthesis. And last, it was difficult to characterize their properties with depth and accuracy. This report also pointed out the key issue, that was to make nanoparticles with uniform size. And my goals were to address these challenges. Specifically, I wanted to improve the synthesis methods so that I could control particle size and to get particle with desired size and with narrow size distribution. I also wanted to manipulate the structure of nanoparticles. To achieve these goals, I made plans. For any synthesis, I think rational design is very important because it helps us get what we want. But to be able to design rationally, we need to know what are happening in the synthesis process and how to control them. So the first thing I planned to do was to study the growing process of nanoparticles. And then develop methods for controllable synthesis of nanoparticles, and then manipulate the structures of nanoparticles. Specifically, I studied gold nanoparticles. To make nanoparticles using wet chemical method, it usually involves metal precursor, reducing agent, solvent, and capping surfactant. Here, as you see, I highlighted the reducing agent for this work. Why? Because it decides how fast the reaction is. If I use a strong reducing agent, then the reaction is very fast, and within minutes, nanoparticles would be formed. And I may not be able to capture the events within that short time. So I used a weak reducing agent, citric acid. The synthesis is really very simple. First, mix all reactants and then heat it. Heat it up to 7 degrees C. At this temperature, the reaction starts. During the reaction, keep stirring the mixture. And because I use the weak reducing agent, reaction can last up to several hours. And that would allow me to track the changes by using time-dependent techniques. For this work, we use 2 techniques. One is ex situ TM, and another one is in situ cells. Both are commonly used to study nano-sized particles. Let's first look at the TM results. In our synthesis method, as mentioned, the temperature is a switch. If it's below 7 degrees C, the reaction will be stopped. So I could stop the reaction at any stage. And if I characterize them by TM, I would know the size change of the particle during the synthesis. As you can see here, the color of the solution changes with time. At 0 minute, the color is light yellow. At 30 minute, the color is a little bit darker. However, at 30 minute, we took the TM image, but we cannot see anything. At 120 degrees C, at 120 minutes, the solution is no more clear. From TM images, big particles could be observed. I was very interested in the events occurring before 30 minutes because that will help determine the reaction paths. According to our previous work, there could be two paths. One could be that the metallic ions are fully reduced into the zero-valent atoms first, and then aggregate into nuclei and grow into nanoparticles. That is path 1 here, and this is the classical path of nucleation. Or it could be that the metal ions form cluster complex first, and then reduced to metallic clusters, and that is path 2 here. To know which path it is, I need to take the metal species at the early stage. We therefore performed in situ self-measurements. This is our in situ setup. The reaction happens in this flask, and we used a peristaltic pump to continuously deliver the solution to the in situ cell and then back to the container. At the same time, the time-dependent self-spectra were collected, and as you can see here, the data were collected in transmission mode. This slide shows gold air 3H self-spectra. We know self-spectra could be divided into thens and ESAFs. So here I have thens and also K-space ESAFs and R-space ESAFs. By looking at the time-dependent thens spectra, you could see that with increase of time, the intensity of the white light, this intense peak, decreases and finally gets close to that of gold foil. That suggests the reduction of gold species with the reaction time. Not only in thens, we could also see the reduction from the ESAF spectra. In K-space, starting from 210 minutes, we observe changes in K-space. And in R-space, you could see that at the beginning, there's a distinct peak at about 1.8 angstrom, and that is due to gold chlorine contribution. With time, this peak decreases. At the same time, there are new peaks going up between 2 and 3 angstrom. These new peaks are due to gold contribution, and that means gold nanoparticles are formed. As mentioned, we know what happens after 120 minutes. We see particles in the TM images, but we wanted to know what is happening at the early stage of growing. And for that, TM could not help. But from SAF's spectra, we noticed some changes. For instance, in thens, except for the change of the white light, there's also subtle change here. And in R space, ESAFs at the early stage, though it's weak, there are also peaks between 2 and 3 angstrom, and they grow with time. And interestingly, we notice that compared to the gold foil, the dashed line, the peak locates at higher R for our sample. To get quantitative structure information, we performed ESAF's data analysis. Here shows a change of the gold bond distance with time. As you can see here, it can actually be divided into 3 stages. In the first stage, for 60 minutes, the distance is longer than that in gold foil. For gold foil, the dashed line indicates the bond distance is about 2.87 angstrom. And also, in the stage 1, the distance decreases with time. In the second stage, between 60 and 160 minutes, the distance keeps decreasing with time, and they are smaller than that in gold foil. The smaller distance suggests the formation of small clusters. In the third stage, after 160 minutes, the distance increases. That suggests the growing of clusters. Now the question is why the distance is long in the first stage. And our hypothesis is that there's new gold species there. To confirm it and to determine the structure of this species, we did dense simulations. We collected all possible structures published in previous work and simulated their dense spectra, and found that the possible species is this dimer. As you can see here in this dimer, gold is not completely reduced. So from the precursor to this dimer, gold is just partially reduced. In addition to the information of bond distance, we also obtained a change of coordination numbers for gold, chlorine, and gold-gold. As expected, the coordination number of gold-chlorine decreases, while the coordination number of gold-gold increases with time. And the changing trend could also be divided into 3 stages. Stage 1 is early nucleation, formation of dimers and trimers. Stage 2 is slow growth of small clusters. And stage 3 is the formation of large particles. And in this stage, the growth rate is high. In addition to that, according to our dense simulation results, we believe path 2 is preferred in the nucleation stage. This work determined the nucleation path and the structure of gold species in the early stage. It actually also provided me some ideas about how to improve the synthesis method so that I can control the particle size and the distribution. I think to get narrow size distribution, I need to pay more attention in stage 1, in the early nucleation formation stage. And to get small clusters, stage 2. You'll hear the particle, in this stage, the clusters grow slowly. And to get larger particles, stage 3. At this stage, large particles are formed. So I designed a synthesis method. I used different precursor, solvent, and reducing agent and surfactant. They're listed here. I'll explain why I use these chemicals at the end. And now I want to show you what I obtained using this method. So this table shows how much chemicals I used for the synthesis. And the synthesis is very easy. Mix everything except for the surfactant, stirring and no heating. And the surfactant was added at a different time. Depending on when I add the surfactant, particles with different size were expected to be obtained. And the characterization methods are TM, UVVs, and in situ dense. Here are the TM images. As you can see here, it looks like I obtained what I wanted. I obtained particles with different sizes and with narrow distribution. As you can see here at 30 minutes, and 60 minutes, particle size is very small, about 1 nanometer. 600 minutes, about 1.8, and then 2.4, and then 3.3. For the small clusters, they have discrete electronic structure. So in their UVV spectrum, we see multiple peaks. And to tell what is really happening during synthesis, I performed in situ steps. That is our in situ setup. It's a little bit different from the previous one. Here, the reaction occurs in this flask. And once it started at a certain time, I took a little bit of the upper clear solution to the reactor and took the gold R3H subspectra. Again, from setup, you can see the data were collected in transmission mode. This figure shows a time-dependent dense spectra. As you could see, with increase of the reaction time, the self signal changes. The H jump goes up first and then goes down. See, this is precursor. This 2 minute, 8 minute, 20 minute, 28 minute, 38 minute, 48, 58, and then goes down. 86, 157, 240, 300, 420, and 840. And I want to mention that this is the dense spectra and it's not normalized. And if it's normalized, you will not see such change. And also, we know from this equation, you can see the H jump J is proportional to the total content of gold dissolved in the solution. So this results means the gold concentration is changing in the solution during the synthesis. By using this equation, we obtained the gold concentration in the solution. As you can see here, the gold concentration increases with time and reaches the maximum at 58 minutes. After that, it decreases slowly. Now let's see what is happening and how can these results be connected with the synthesis process. In this synthesis, I chose this precursor for several reasons. First, this precursor has low solubility in ethanol. As you can see here, it is only about 1.65 millimole per liter. But the nominal concentration of gold is 17.86. That means the precursor is slowly and continuously supplied to the solution, and that's why the gold concentration increases before 58 minutes. Such self-supplement of precursor helps shift the critical nuclei size back to smaller values and focuses the size distribution. In addition to that, we used a relatively weak reducing agent that also helps improve the size distribution. And also for this precursor, this is how it looks like. The gold is protected by those function groups. And such geometry will also help get small particle size because their geometry stops the aggregation of gold atoms. At 58 minutes, almost all the precursors were transformed into clusters. After that, they grow and sink to the bottom of the flask. That explains why the gold concentration decreases after 58 minutes. To control the particle size, I only need to stop the growing at any time I want. To stop it, I added a strong surfactant. Thiol. It protects the particle and ends the further aggregation of particles. Okay, now that is my second work. As planned, I started the nucleation and the growing process of gold nanoparticles. Based on that, I was able to rationally design the synthesis method, and I obtained what I wanted. I control the particle size. I get particles with narrow distribution. Next, I would like to find a way to control the structure. On my way doing that, an accident happened. My sample was prepared in ethanol, but I accidentally redispersed them into hexane. So I have two samples. One is ethanol sample, one is hexane sample. For both samples, I took UV spectra and then spectra. As you can see here, for the ethanol sample, as we showed before, the cluster, because it's small cluster, and the spectra show discrete. The clusters, the small clusters have discrete electronic structure, so you see multiple peaks here. But when I disperse the particles into hexane, I obtained a spectra kind of featureless. And also, as you can see here, the then spectra are different for the hexane sample and ethanol sample. The UVs and the self-spectra of these two samples told me that something happened, and the samples are different. We also observe the spectral changes in real time. This is the time-dependent dance, and this is time-dependent UVs. For time-dependent dance, you can see that with time, this peak D shifts, and the peak C increases intensity. And even in the time-dependent UV spectra, you can see that there are so many features at the beginning, but with time, they gone. So I was wondering what happened. Is it just because of the solvent effect? So I did little research, and according to the literature, solvent would cause the shift of UV's peak, but it would not change the spectral shape. But as you can see in our UV spectra, the shape changes. Then, my next guess was the size change. I collected TM images of these two samples. Here are two representative images, and here you can see that there's almost no change in particle size. Both are about 1.0 nanometer. Then, my last guess is the structure change. To determine the structure, again, I did dense simulations. I found all possible structures from previous work and simulations of them. And I found the best structure model for the ethanol sample and for the hexane sample. For the ethanol sample, it is a gold 13 cluster in an icosahedral geometry. For the hexane sample, it is also a gold 13 cluster, but in a cubodahedral geometry. Now I know the structure change after I redispersed the cluster to a different solvent. But why? To get some clues about why the structure changes, we analyzed the ESAF's data. The best fitting results were summarized in this table. From the results, you can see that there is a decrease in the coordination number of gold low Z bond upon the change of the solvent. In ethanol, it's about 0.9. In hexane, it's about 0.4. So that means in the hexane, the surfactant partially desorbed, and that caused the structure transformation of gold clusters from icosahedral to cubodahedral. From this work, you can see that we can actually manipulate the structure of clusters by post-treatment. And in this work, I only redispersed the class into a different solvent. Then the structure changed. Last, I like to summarize the work. In summary, I studied the nucleation and the growing of gold nanoparticles. I improved the synthesis method and studied the structural transformation of gold nanoclusters driven by solvent. As you can see, for these studies, in situ salves is the primary technique. Thence, help me determine the concentration of gold species and determine the atomic structure and geometry. ESAFs provided me information of local bonding environment and help to get quantitative local structure information. And that's the end of my sharing, and thank you for your attention.